The laws of science, also called scientific laws or scientific principles, are statements that describe or predict a range of natural phenomena. Each scientific law is a statement based on repeated experimental observations that describe some aspect of the universe. The term law has diverse usage in many cases: approximate, accurate, broad, or narrow theories across all fields of natural science, physics, chemistry, biology, geology, astronomy, etc. Scientific laws summarize and explain a large collection of facts determined by experiment, and are tested based on their ability to predict the results of future experiments. They are developed either from facts or through mathematics, and are strongly supported by empirical evidence. It is generally understood that they reflect causal relationships fundamental to reality, and are discovered rather than invented. Laws reflect scientific knowledge that experiments have repeatedly verified and never falsified. Their accuracy does not change when new theories are worked out, but rather the scope of application, since the equation, if any, representing the law does not change. As with other scientific knowledge, they do not have absolute certainty as mathematical theorems or identities do, and it is always possible for a law to be overturned by future observations. A law can usually be formulated as one or several statements or equations, so that it can be used to predict the outcome of an experiment, given the circumstances of the processes taking place. Laws differ from hypotheses and postulates, which are proposed during the scientific process before and during validation by experiment and observation. Hypotheses and postulates are not laws since they have not been verified to the same degree and may not be sufficiently general, although they may lead to the formulation of laws. A law is a more solidified and formal statement, distilled from repeated experiment. Laws are narrower in scope than scientific theories, which may contain one or several laws. Science distinguishes a law or theory from facts. Calling a law a fact is ambiguous, an overstatement, or an equivocation. Although the nature of a scientific law is a question in philosophy, and although scientific laws describe nature mathematically, scientific laws are practical conclusions reached by the scientific method. They are intended to be neither laden with ontological commitments nor statements of logical absolutes. According to the unity of science thesis, all scientific laws follow fundamentally from physics. Laws which occur in other sciences ultimately follow from physical laws. Often, from mathematically fundamental viewpoints, universal constants emerge from a scientific law. Overview. A scientific law always applies under the same conditions, and implies that there is a causal relationship involving its elements. Factual and well-confirmed statements like, "Mercury is liquid at standard temperature and pressure," are considered too specific to qualify as scientific laws. A central problem in the philosophy of science, going back to David Hume, is that of distinguishing causal relationships such as those implied by laws from principles that arise due to constant conjunction. Laws differ from scientific theories in that they do not posit a mechanism or explanation of phenomena, they are merely distillations of the results of repeated observation. As such, a law is limited in applicability to circumstances resembling those already observed, and may be found false when extrapolated. Ohm's law only applies to linear networks, Newton's law of universal gravitation only applies in weak gravitational fields, the early laws of aerodynamics such as Bernoulli's principle do not apply in case of compressible flow such as occurs in transonic and supersonic flight, Hooke's law only applies to strain below the elastic limit, etc. These laws remain useful, but only under the conditions where they apply. Many laws take mathematical forms, and thus can be stated as an equation. For example, the law of conservation of energy can be written as delta E equals 0 display style delta E equals 0, where E is the total amount of energy in the universe. Similarly, the first law of thermodynamics can be written as d U equals delta Q minus delta W display style mathrm d U equals delta Q delta W. The term scientific law is traditionally associated with the natural sciences, though the social sciences also contain laws. An example of a scientific law in social sciences is Zipf's law. Like theories and hypotheses, laws make predictions. Specifically, they predict that new observations will conform to the law, and can be falsified if they are found in contradiction with new data. Conservation laws. Conservation and symmetry. Most significant laws in science are conservation laws. These fundamental laws follow from homogeneity of space, time and phase, in other words symmetry. Noether's theorem, any quantity which has a continuous differentiable symmetry in the action has an associated conservation law. Conservation of mass was the first law of this type to be understood, since most macroscopic physical processes involving masses, for example collisions of massive particles or fluid flow, provide the apparent belief that mass is conserved. Mass conservation was observed to be true for all chemical reactions. In general this is only approximative, because with the advent of relativity and experiments in nuclear and particle physics, mass can be transformed into energy and vice versa, so mass is not always conserved, but part of the more general conservation of mass energy. Conservation of energy, momentum and angular momentum for isolated systems can be found to be symmetries in time, translation, and rotation. Conservation of charge was also realized since charge has never been observed to be created or destroyed, and only found to move from place to place. Continuity and transfer. Conservation laws can be expressed using the general continuity equation for a conserved quantity can be written in differential form as ρ t equals minus j display style frac partial ρ partial t equals nabla cdot math bf j, where ρ is some quantity per unit volume, j is the flux of that quantity, change in quantity per unit time per unit area. Intuitively, the divergence denoted of a vector field is a measure of flux diverging radially outwards from a point, so the negative is the amount piling up at a point, hence the rate of change of density in a region of space must be the amount of flux leaving or collecting in some region. See main article for details. In the table below, the fluxes, flows for various physical quantities in transport, and their associated continuity equations, are collected for comparison. More general equations are the convection diffusion equation and Boltzmann transport equation, which have their roots in the continuity equation. Laws of classical mechanics. Principle of least action. All of classical mechanics, including Newton's laws, Lagrange's equations, Hamilton's equations, etc., can be derived from this very simple principle: delta S equals delta T 1 T 2 L Q Q T D T equals 0. Display style delta math call S equals delta int underscore T underscore 1 caret T underscore 2 L math BF Q math BF dot Q T DT equals 0, where S display style math call S is the action, the integral of the Lagrangian L Q Q T equals T Q T minus V Q Q T. Display style L math BF Q math BF dot Q T equals T math BF dot Q T V math BF Q math BF dot Q T of the physical system between 2 times T1 and T2. The kinetic energy of the system is T, a function of the rate of change of the configuration of the system, and potential energy is V, a function of the configuration and its rate of change. The configuration of a system which has n degrees of freedom is defined by generalized coordinates q equals q1, q2, qn. There are generalized momenta conjugate to these coordinates, p equals p1, p2, pn, where P I equals L Q I display style P underscore I equals frac partial L partial dot Q underscore I. The action and Lagrangian both contain the dynamics of the system for all times. The term path simply refers to a curve traced out by the system in terms of the generalized coordinates in the configuration space, i.e. the curve Q t, parameterized by time. See also parametric equation for this concept. The action is a functional rather than a function, since it depends on the Lagrangian, and the Lagrangian depends on the path Q t, so the action depends on the entire shape of the path for all times in the time interval from t1 to t2. Between two instants of time, there are infinitely many paths, but one for which the action is stationary to the first order is the true path. The stationary value for the entire continuum of Lagrangian values corresponding to some path, not just one value of the Lagrangian, is required. In other words, it is not as simple as differentiating a function and setting it to zero, then solving the equations to find the points of maxima and minima etc. Rather, this idea is applied to the entire shape of the function. See calculus of variations for more details on this procedure. Notice L is not the total energy E of the system due to the difference, rather than the sum E equals T plus V. Display style E equals T plus V. The following general approaches to classical mechanics are summarized below in the order of establishment. They are equivalent formulations. Newton's is very commonly used due to simplicity, but Hamilton's and Lagrange's equations are more general, and their range can extend into other branches of physics with suitable modifications. From the above, any equation of motion in classical mechanics can be derived. Corollaries in mechanics: Euler's laws of motion, Euler's equations, rigid body dynamics, corollaries in fluid mechanics. Equations describing fluid flow in various situations can be derived using the above classical equations of motion and often conservation of mass, energy and momentum. Some elementary examples follow. Archimedes' principle, Bernoulli's principle, Poiseuille's law, Stokes's law, Navier-Stokes equations, Faxon's law. Laws of gravitation and relativity. Modern laws. Special relativity. Postulates of special relativity are not laws in themselves, but assumptions of their nature in terms of relative motion. Often two are stated as, "The laws of physics are the same in all inertial frames," and "The speed of light is constant." However, the second is redundant, since the speed of light is predicted by Maxwell's equations. Essentially there is only one. The said postulate leads to the Lorentz transformations, the transformation law between two frame of references moving relative to each other. For any four-vector A equals lambda A displaystyle A equals lambda A. This replaces the Galilean transformation law from classical mechanics. The Lorentz transformations reduce to the Galilean transformations for low velocities much less than the speed of light c. The magnitudes of four vectors are invariants, not conserved, but the same for all inertial frames, i.e. every observer in an inertial frame will agree on the same value. In particular, if A is the four momentum, the magnitude can derive the famous invariant equation for mass energy and momentum conservation. See invariant mass. E 2 equals P C 2 plus M C 2 2. Display style E caret 2 equals PC caret 2 plus Mic caret 2 caret 2, in which the more famous mass energy equivalence E equals Mic 2 is a special case. General relativity is governed by the Einstein field equations, which describe the curvature of spacetime due to mass energy equivalent to the gravitational field. Solving the equation for the geometry of space warped due to the mass distribution gives the metric tensor. Using the geodesic equation, the motion of masses falling along the geodesics can be calculated. Gravitomagnetism, a relatively flat spacetime due to weak gravitational fields. Gravitational analogues of Maxwell's equations can be found, the GEM equations, to describe an analogous gravitomagnetic field. They are well established by the theory, and experimental tests form ongoing research. Classical laws. Kepler's laws, though originally discovered from planetary observations also due to Tycho Brahe, are true for any central forces. Thermodynamics. Newton's law of cooling. Fourier's law. Ideal gas law, combines a number of separately developed gas laws. Boyle's law. Charles's law. Gay-Lussac's law. Avogadro's law, into one now improved by other equations of Stadler-Dalton's law of partial pressures. Boltzmann equation. Carnot's theorem. Kopp's law. Electromagnetism. Maxwell's equations give the time evolution of the electric and magnetic fields due to electric charge and current distributions. Given the fields, the Lorentz force law is the equation of motion for charges in the fields. These equations can be modified to include magnetic monopoles, and are consistent with our observations of monopoles either existing or not existing. If they do not exist, the generalized equations reduce to the ones above; if they do, the equations become fully symmetric in electric and magnetic charges and currents. Indeed, there is a duality transformation where electric and magnetic charges can be rotated into one another and still satisfy Maxwell's equations. Pre-Maxwell laws. These laws were found before the formulation of Maxwell's equations. They are not fundamental, since they can be derived from Maxwell's equations. Coulomb's law can be found from Gauss' law, electrostatic form, and the Biot-Savart law can be deduced from Ampere's law, magnetostatic form. Lenz's law and Faraday's law can be incorporated into the Maxwell-Faraday equation. Nonetheless, they are still very effective for simple calculations. Lenz's law, Coulomb's law, Biot-Savart law, Lawson's law, Kirchhoff's laws, Joule's law. Photonics. Classically, optics is based on a variational principle. Light travels from one point in space to another in the shortest time. Fermat's principalline geometric optics laws are based on approximations in Euclidean geometry, such as the paraxial approximation. Law of reflection. Law of refraction, Snell's law in physical optics. Laws are based on physical properties of materials. Brewster's angle. Malice's law. Beer-Lambert law. In actuality, optical properties of matter are significantly more complex and require quantum mechanics. Laws of quantum mechanics. Quantum mechanics has its roots in postulates. This leads to results which are not usually called laws, but hold the same status, in that all of quantum mechanics follows from them. One postulate that a particle or a system of many particles is described by a wave function, and this satisfies a quantum wave equation, namely the Schrödinger equation, which can be written as a non-relativistic wave equation, or a relativistic wave equation. Solving this wave equation predicts the time evolution of the system's behavior, analogous to solving Newton's laws in classical mechanics. Other postulates change the idea of physical observables. Using quantum operators, some measurements can't be made at the same instant of time. Uncertainty principles. Particles are fundamentally indistinguishable. Another postulate, the wavefunction collapse postulate, counters the usual idea of a measurement in science. Topic: Radiation laws. Applying electromagnetism, thermodynamics, and quantum mechanics, to atoms and molecules, some laws of electromagnetic radiation and light are as follows. Stefan Boltzmann law, Planck's law of black-body radiation, Wien's displacement law, radioactive decay law. Laws of chemistry. Chemical laws are those laws of nature relevant to chemistry. Historically, observations led to many empirical laws, though now it is known that chemistry has its foundations in quantum mechanics. Quantitative analysis. The most fundamental concept in chemistry is the law of conservation of mass, which states that there is no detectable change in the quantity of matter during an ordinary chemical reaction. Modern physics shows that it is actually energy that is conserved, and that energy and mass are related, a concept which becomes important in nuclear chemistry. Conservation of energy leads to the important concepts of equilibrium, thermodynamics, and kinetics. Additional laws of chemistry elaborate on the law of conservation of mass. Joseph Proust's law of definite composition says that pure chemicals are composed of elements in a definite formulation. We now know that the structural arrangement of these elements is also important. Dalton's law of multiple proportions says that these chemicals will present themselves in proportions that are small whole numbers, i.e. 1 to 2 for oxygen, hydrogen ratio in water, although in many systems, notably biomacromolecules and minerals, the ratios tend to require large numbers and are frequently represented as a fraction. More modern laws of chemistry define the relationship between energy and its transformations. Reaction kinetics and equilibrium. Molecules exist in mixture defined by the transformations possible on the timescale of the equilibrium, and are in a ratio defined by the intrinsic energy of the molecules. The lower the intrinsic energy, the more abundant the molecule. Le Chatelier Principle states that the system opposes changes in conditions from equilibrium states, i.e. there is an opposition to change the state of an equilibrium reaction. Transforming one structure to another requires the input of energy to cross an energy barrier. This can come from the intrinsic energy of the molecules themselves, or from an external source which will generally accelerate transformations. The higher the energy barrier, the slower the transformation occurs. There is a hypothetical intermediate, or transition structure, that corresponds to the structure at the top of the energy barrier. The Hammond-Leffler postulate states that this structure looks most similar to the product or starting material which has intrinsic energy closest to that of the energy barrier. Stabilizing this hypothetical intermediate through chemical interaction is one way to achieve catalysis. All chemical processes are reversible, law of microscopic reversibility. Although some processes have such an energy bias, they are essentially irreversible. The reaction rate has the mathematical parameter known as the rate constant. The Arrhenius equation gives the temperature and activation energy dependence of the rate constant, an empirical law. Thermochemistry-Dulong-Petit law. Gibbs-Helmholtz equation. Hess's Lagrange-Raoult's law. Henry's law. Chemical transport. Fick's laws of diffusion. Graham's law. Lamb equation. Topic: Geophysical laws. Archie's law, Buys-Ballott's law, Birch's law, Byerly's law. Topic: See also. Topic: References. Topic: Further reading. Topic: External links. Physics Formulary, a useful book in different formats containing many or the physical laws and formulae. eFormulae.com, website containing most of the formulae in different disciplines. Media related to scientific laws at Wikimedia Commons.
Hi there. I'm enjoying your takedown of Rappaport, but I've just got a small correction for you. In part 2, you said that the difference between a scientific theory and a scientific law is that a scientific law is the old word for what we now call a scientific theory. That's not quite right. A scientific law refers to one simple or fairly concise statement about how a thing works. A theory is much broader and will explain much more about the phenomenon in question. So a theory will contain one or more laws, but it will be a wider explanation, a wider model. So if you take the example of Newton, the law of gravity is simply stated. The gravitational attraction between two bodies is equal to the gravitational constant times the mass of the first object times the mass of the second object divided by the distance between them squared. It's called the Law of Universal Gravitation. Ironically, Newton didn't really have a good theory of gravitation because he never actually decided or knew what was going on. He understood there was some sort of action at a distance going on, but he couldn't explain any mechanism for that and didn't really understand how it was happening. So his theory was at best incomplete. So the theory is a broader conceptual statement of the phenomena in question, where a law is a narrow statement which defines one aspect of that phenomenon in question. What you said about the historical dropping out of favour of the word law is also true, by the way. I'm just saying there's a little bit more to it. And I think theory is generally preferred nowadays, but they aren't the same thing, and I think if I don't point it out, then somebody else might. I hope this helps. Keep up the good work.
Welcome to an explainer on phenomenology. At its most basic, phenomenology is the study of lived experience. As its name suggests, phenomenology is concerned with the study of phenomena that arise from the experience of being in the world. The development of modern phenomenology, established by Edmund Husserl in the early 20th century, was a break from the Cartesian system that pitched stark distinctions between the outer, real reality and the individual experience of reality. Following the Cartesian principle, outer reality is a separate and distinct entity that can only be understood in rational terms through cognitive processes of deduction. Sense perception was thought to distort this process, and certainly emotions were considered a lower form of experience emanating from the recesses of the body. In contrast, phenomenology seeks to understand the outside world as it is interpreted by and through human consciousness. Ontologically speaking, that means speaking in terms of how philosophers understand the nature of being and existence, Husserl purported that reality could be grasped by and through structures of consciousness, by applying what he called intentionality to the object of study, or intentionally directing one's focus to describe realities. For Husserl, to achieve deeper understanding of an object of study, a researcher could quarantine their personal judgments, a process called bracketing, so that preconceived notions do not interfere with the phenomenological inquiry. It is at this point that Martin Heidegger's approach breaks with Husserl's process. In fact, Heidegger was very critical of Husserl's phenomenology, where Husserl sought to capture objects of study as graspable entities that could be objectively studied. Heidegger employed the notion of Dasein, the situated meaning of a human in the world. For Heidegger, consciousness is a product or construction of the historical context from which it arises, and in turn, one can never approach an object of study in a presuppositionless form. That is, objects of study cannot be neatly separated from their contexts, nor should they be. Reality and consciousness are co-creations, and because of this, human understanding always arises from the relationship between the two acting upon each other. Thank you for watching.
What is an empirical study? Put simply, an empirical study can be defined as a collection and analysis of primary data to answer a research question. The study is then reported in an article by the researchers who conducted the experiment. How the experiment is carried out can differ in criteria, from qualitative to quantitative. However, all empirical studies include a number of things that can help identify them. To determine whether or not a study is an empirical study, there are some questions you can ask. Is there a specific research question? Empirical studies present primary data collection with the intention of answering a previously determined research question, so keep an eye out for the question being answered in the abstract or the introduction. Can the study be replicated? When reading through the methodology section, ask yourself if the experiment or survey can be replicated. Also try to determine their methodology. Empirical studies consist of hands-on research, which can vary from surveys to social experiments. Let's take a look at an example. Reading through this article's abstract, some things pop out right away that lead me to believe the study is empirical. The first being a question that needs answering. What's the association of depression with grief-related risk factors among bereaved individuals? The second thing I notice in the method section is a clear population and primary study method. We can see that the mode of research was a primary interview among 161 individuals. The research question mixed with a hands-on study characterizes this source as being empirical. Also, a quick mention, some databases make finding empirical studies really easy, such as PsycInfo, which allows you to narrow to empirical studies using the Refine Results tab on the left side of the page. So, what isn't empirical research? Some common examples of scholarly papers that aren't empirical studies are literature reviews and papers that form theories based on the research of others. Let's take a look at some examples. This paper doesn't appear to be a literature review, as it has a clear, unexplored topic which it wishes to expand on. However, one thing mentioned in just the third sentence of the abstract that leads me to believe that the article isn't empirical is the statement, "This effort is correlated with the newest research findings in cognitive neuroscience and neurocognitive psychology of creativity." With this, it's apparent that they won't be conducting any primary research on their own, but will instead draw from other relevant research that has already been conducted. There's further evidence from the fact that, scrolling through their paper, there's no methodology section. This paper seems more interested in developing a theory to explain previous research rather than conducting new research to answer a question, making it a non-empirical study. Overall, the main giveaways to a study being empirical are a clear research question and primary, repeatable data collection, which can range from surveys to social experiments. If you need more help with empirical studies, feel free to ask a librarian.
Either within a research or within
What
a
is an
philosophy,
empirical
you are
study?
going to meet the terms
Put simply,
of
an empirical study
and
can be defined as a
non-empirical
collection and analysis of
research.
primary
Let's take a
data
look
to
on
answer a
what
research
does this
question.
to mean. And I will draw
The study is
myself
then
a
reported
line
in an
that I
article
think
by the
will help us
researchers
a
who
lot.
conducted the
And on
experiment.
its left side, I'm
How the
going to
experiment is
have
carried out can
a
differ in
purely
criteria, from
empirical
qualitative to
research. So here will
quantitative.
be purely
However, all empirical studies include a number of
purely
things that can help identify them.
empirical research.
To determine whether or not a study is an empirical
And of
study,
course, on the other
there are some
side,
questions
I'm
you can
going to
ask.
have purely,
Is there a specific research
purely,
question?
and these two terms, or
Empirical
these terms
studies
going to
present
be
primary
very
data
important for us.
collection with the intention of answering a
Non-empirical.
previously determined research question.
Empirical.
So keep an
What
eye out
does
for
it
the
mean
question
to
being
say
answered in the abstract
empirical?
or the
What is
introduction.
the synonym that you can
Can the
make
study
it
be
the
replicated?
easiest find out?
When
The
reading through the
synonym of this
methodology
word is
section,
going to be,
ask yourself if the
it is
experiment or
based
survey can be
on some
replicated.
experience.
Also try to determine their
Experience.
methodology.
And what
Empirical
is the
studies
opposite
consist of
experience? If
hands-on
you are going
research,
to graduate
which can vary from
school,
surveys to
you
social
have no
experiments.
experience, but on the other
Let's take a
hand,
look at
you
an
have
example.
some theoretical knowledge. So you can say
Reading
a
through this
theory.
article's abstract, some
And
things
the
pop
same
out
is
right
going
away
to
that lead me
apply
to
on
believe the
this our
study is
bipolar
empirical.
line.
The
If
first
you
being
are
a
going
question
to
that
do
needs
a
answering.
purely empirical
What's the
research, you are
association
going
of
to
depression with
rely on
grief-related
some
risk factors
facts,
among bereaved
on some
individuals?
facts, on some
The
experience
second thing I notice in
you
the
have
method
or
section
something
is a clear
you have
population and
observed
primary study method.
or you have observed,
We can see that the mode of research
but
was a
you are
primary interview
not
among
going to have any
161
kind of
individuals.
theory within your research.
The
So
research
the
question
purely
mixed with a
empirical
hands-on
research
study
cannot really
characterizes
exist
this source as
because
being
you are
empirical.
not producing
Also,
anything,
a quick mention,
so nothing,
some databases make finding
nothing
empirical studies really easy,
meaningful,
such as PsycInfo,
meaningful,
which allows you to narrow to empirical
meaningful.
studies using the
And
Refine
on the other
Results
hand,
tab
we
on
have
the
got
left side of the
purely
page.
non-empirical research, so
So,
we would
what
base
isn't empirical
all our
research?
research and all our
Some
papers
common
just
examples of
about
scholarly
some
papers that
theory,
aren't empirical studies
theories,
are
some
literature reviews
models,
and papers that form
some
theories based on the
models,
research
but
of
we
others.
would have
Let's take a look at some examples.
no proofs
This
that
paper
our
doesn't appear to
theories
be
are
a
really
literature
true.
review,
So a
as it has a
purely
clear,
non-empirical
unexplored
research
topic which it
cannot
wishes
really
to expand
exist.
on.
And when we are going to do a research,
However,
we are going to
one
be
thing mentioned
somewhere
in just the
between.
third sentence
So
of the
our
abstract
research
that
is
leads
going
me
to
to
be
believe
here.
that the article isn't
If
empirical
you
is
are,
the
or
statement,
you can meet
"This effort is
sometimes
correlated with the
almost
newest
the
research
purely
findings in cognitive neuroscience and
non-empirical research,
neurocognitive
and those are
psychology of
called
creativity."
literature reviews.
With this, it's
Literature
apparent that they won't be conducting any primary
literature
research on their
reviews.
own, but will
These are
instead
the
draw from
papers
other relevant
when
research that
almost
has already
every
been conducted.
sentence is referenced.
There's
At
further
the end
evidence
of
from the
the
fact that,
sentence, you can see
scrolling
the
through their
reference to
paper,
the author
there's
and
no
the
methodology
year.
section.
So these are the
This paper
most
seems more interested in developing a
non-empirical
theory to
researches
explain
you are
previous
going to do. But
research
basically, our
rather than
research is
conducting
going to
new
be
research to
somewhere
answer a question,
between these two
making it a
extremes,
non-empirical
between
study.
empirical and non-empirical.
Overall,
the goal of an empirical study is to answer research questions through observation or experimentation. Empirical studies can be quantitative or qualitative, and it's important to understand the difference. In this video, we'll explore characteristics of quantitative and qualitative scholarly articles in order to understand these different approaches to research. Let's start by comparing the goals of quantitative and qualitative approaches. When you think quantitative, think experimental and statistical. The goal here is to measure, test, predict, and describe using statistics. If you conduct a statistical analysis of the correlation between a child's participation in a Head Start program and their likelihood of going to college, you're taking a quantitative approach. But if you go into a preschool classroom, observe children playing, and conduct open-ended interviews with children and teachers about classroom behaviors, you're taking a qualitative approach. Qualitative approaches are naturalistic and interpretive. You might hear terms like ethnographic or phenomenological to describe qualitative research. The goal here is to richly describe people's behaviors and realities rather than to quantify or measure them. Since the goals of quantitative and qualitative studies are different, their methods and data are different too. A quantitative study might use experiments, surveys, or questionnaires, analysis of large datasets like U.S. Census data, or structured interviews and observations, where questions and observation criteria are exactly the same for each participant. Data in a quantitative study is numerical in the first place, or is quantifiable. The qualitative study might use field research, case studies, or more open-ended interviews and observations, where there is more room for flexibility and follow-up. The data in a qualitative study might be interview or focus group transcripts, observation notes, or journal entries. Because methods are different, data analysis techniques also vary between quantitative and qualitative studies. Quantitative studies will feature statistical analyses, while qualitative studies might use text analysis and a coding for themes in order to interpret data. While you'll probably see more numbers, charts, and graphs in a quantitative study, be careful. Just because you see these doesn't automatically mean the study is quantitative. Qualitative studies might report basic demographic information numerically before diving into qualitative analysis. So it's always important to read the study for additional information. Let's take a look at some examples. Here are 3 studies about adolescent mental health. We'll focus on their goals, methods, data, and data analysis techniques to determine if they are quantitative or qualitative. Our first study is about depression in female adolescents. According to the article, the goal of this exploratory study was to gain an understanding of female adolescents' own experiences of depression and give voice to their experiences. The method for doing this was 6 open-ended interviews regarding participants' experiences of depression. The data consisted of interview transcripts, and the article includes quotes from the interviews. The data analysis technique was interpretive phenomenological analysis, in which researchers distilled themes from the interview transcripts. This is an example of a qualitative study. Our second example is about sleep issues as a risk factor for suicidal behavior in depressed children and adolescents. According to the article, the goal of this study was to investigate the association between sleep complaints and suicidal behaviors in this population. The method for doing this was through a structured interview about sleep, the same questions for every participant, plus 2 tests, the Children's Depression Rating Scale and the Children's Global Assessment Scale. The data consisted of frequency of sleep issues from the interviews, as well as a numerical score for the 2 scales. The researchers used statistical analysis to analyze the data and presented the information about the correlation between variables using tables. This is an example of a quantitative study. Our last example is about self-labeling among adolescents with mental disorders, or the impact of mental illness labels on teens' psychological well-being. According to the article, the goal of this study was to investigate associations between self-labeling and perceived negative treatment by others, clinical and demographic factors. The researchers had the hypothesis that many teens wouldn't self-label, and those that did would have worse psychological well-being. The researchers combined methods to test this hypothesis. They did semi-structured interviews with some open-ended questions where teens could express their thoughts and emotions. They also used rating scales to quantify teens' experiences like the Rosenberg Self-Esteem Scale and clinical information about each patient, like their type of disorder and age of first treatment for mental health issues. The data in this study consisted of interview transcripts, scores from the scales, and clinical information. Because researchers combined methods, they also needed to use several data analysis techniques. The researchers used textual analysis to find themes in the interview transcripts, and they ran statistical analyses for relationships between the variables on the scales and the clinical information. The articles included quotes from the teens, as well as statistical tables. Because this study uses both qualitative and quantitative methods, we call it a mixed methods study. So, what makes a better empirical study? Quantitative studies aren't automatically better or worse than qualitative studies. These two approaches are just different. Sometimes researchers even combine approaches to present a fuller picture through a mixed methods study. When you're evaluating a study's approach, ask yourself, how well do the methods and analyses fit the research question? If you need help with quantitative, qualitative, and mixed methods studies, you can always ask a librarian.